Is there any of your friend who you know is just about to come? Then we can wait for a minute. You have someone coming? Okay, so we studied about pointer analysis in the previous session. We discussed how pointer analysis allows to construct a kind of stack and heap approximation of the actual runtime program. We abstracted out objects using a particular abstraction called as the allocation site abstraction. And then we had also seen how do you update the points to information in terms of the stack and the heap maps as you process each statement, right? Finally, we had looked into some examples of what kinds of optimizations you might be able to perform if the compiler performs pointer analysis or maintains pointer information. In general, as I told you, pointer analysis is one of the most useful data flow analysis for a language that supports pointers, whether it is Java or C, C with structures, let's say, and address of operators, or it's C++ with objects allocated on the heap, or Java in this case where objects are allocated on the heap, and so on. So what we would do now is we would learn a representation of points to information called as the points to graph. Okay, I just want to check with you before we move ahead, is my handwriting legible to you here? Yeah, okay. So points to graph or PTG is just another way of computing pointer information, and it's graphical so you can see it. And third thing finally is you can perform reachability based analysis pretty easily. Since you have a graph, you can perform reachability checks pretty quickly, and we would see it allows us to perform various optimizations. So let's now try to draw points to graphs for some examples that we have. Let's say here we had, this was our original example, a is equal to new a, then a dot f is equal to new b, a dot f dot g is equal to new c, c is equal to a dot f dot g, d is equal to a, e is equal to a dot f, and p is equal to new a. We had some names given to these objects. So this one was let's see, this one was O1, this was O2, this is O3, and this was line number 7, so this is O7. These were the names we had given to different objects here. And now what we can do is, as we process each statement, we can keep drawing points to relationships in the form of a graph. Let us say we draw circles to represent variables and rectangles or squares to represent objects. Okay, and now let's say there are, so these are nodes. You remember I had said you should ask someone the question, what is a node in the graph and what is an edge in the graph, whenever somebody comes up with a new notation for new graph structure. So here this is a variable node and this is an object node, let's say. And then we can have edges. We have two kinds of edges here. Can a variable point to another variable in Java? No, right? In C, you can take the address of a variable and say, oh, star A is equal to ampersand, or A is equal to ampersand of B if you have declared A as a pointer in star A, and then you can say A is equals ampersand of B. But in Java, you cannot take the address of variables. So you cannot really have edges. If you are designing a points to graph where variables are circular, then there is no edges, no edge from one circle to another circle. That's an invariant over here, right? So you can have two kinds of edges here. One from a variable node to an object node. Okay, let's give this object some name, OX. And second kind of edges may be there between objects. So you have, let's say, an object OX here and another object OY here. If one of the fields of OX points to OY, then let's add an edge between them, a directed edge between them, and label the edge with the name of the field. Okay, are all of you with me? So we have two kinds of variables, two kinds of nodes, variable nodes and object nodes. Objects are abstract objects based on our allocation site abstraction, and we have two kinds of edges, one that connects stack variables to objects. This is basically, this would correspond to one entry of our stack map that we had created, maintained in the morning. And then we have another edge. Let's call this a stack edge and let's call this a heap edge. A heap edge is from one object to another object with a label, and the label tells us the name of the field. Which object's field? OX or OY's? OX's, right? So this gives me the name of the field of the object OX that points to OY. Instead of writing it inside here, two names associated with one box will confuse us. Hence I have labeled it like this. If this object also points to another object through another edge G, then we will, another field G, then we will say it like this. Oh, OX dot G points to OZ. Okay. So you can have multiple outgoing edges. Can you have multiple outgoing edges with the same label? Why not? Yeah, it can, no? That's why we had sets of objects, right? The question is, can I have multiple outgoing edges with the same label from an object? Yeah, right. So we had seen after if else branches and so on, merges. That's why we had sets on the right hand side, right? Which means you may have a points to graph in which a variable A points to OX as well as, let's say, some OY. This is possible. Similarly, it's possible that OX dot F points to OY as well as points to OZ. This is possible, no? Why do you say it's not possible? Just before the break, we had said that we can have multiple objects in the set of points to values, points to objects pointed to by a particular variable or a field, right? So that's what is represented by this, right? This just means that OX dot F, the points to set of OX dot F contains two objects, OY and OZ, right? And how did you arrive at this kind of a code? We had seen you have if and else branches. Let's say in one branch you allocate it to something, in else branch you allocate it to something else. After the merge point you would get both of them, you will take a union, right? So the merge operation is union in case of pointer analysis as well over here. Is that clear to all of you? So just be sure that this is not an incorrect points to graph. This is just a representation of the fact that we can have sets of, or we have essentially sets of objects that can be pointed to by a variable or the field of another object, right? That's what we had. Any questions before we move ahead? So now what we'll do is, oops. Yeah. Now let's come back to this piece of code here. We have these 7 statements, and how do you usually perform an iterative data flow analysis? You process each statement, you update the inset and the outset, either the inset based on the outset if it's a backward analysis, or the outset based on the inset if it's a forward analysis, and then you keep on updating this until fixed point for all the statements, right? So let's now construct the points to graph for all the statements based on this piece of information. So here after line 1, let me also give numbers. After line 1, line 2, 3, 4, 5, 6, 7. Now I'll update the points to graph in place. I'll not draw 14 points to graphs here. I'll just draw one and keep updating it after each point of time. But if you save it, it's basically the in points to graph and the out points to graph. I hope you can make sense of it, but ask me if you're confused. So what's the points to graph? What's the in of 1? What's the points to graph before you start? It's empty. There is nothing, no nodes, no edges. Then once you process statement 1, let's say we create, okay, let's make it a bit more interesting, bit more, or rather bit more explicit. So let's say I have a statement, forget about the code for some more time. I have a statement L is equal to new, some new t. What's the update in the points to graph that I should do to reflect what happens at this statement? L starts pointing to a new object. Let's say it's allocated at L. So then we would create a variable node L here, an object named OL. Let's keep writing them inside itself if you want for consistency, and then we'll create an edge from L to OL. Does that make sense? So here there was nothing, and now this is the updated points to graph. Let me in fact create partitions here. So this part is the statement, this is the existing graph which is empty in this case, or we don't care rather, and here this is the new updated graph after processing this statement. We are just updating the same stack and heap points to relationships, but in the form of a graph now. Okay. Now if the statement is, let's say, L is equal to V, and we have V here which is pointing to some object beforehand, and L also is here, L is pointing to some object beforehand, let's say, whether it points to something or not. What do you do after processing this statement? What should L point to after this statement? Where V points to, right? So the previous edge will be killed. So we'll just say L and V both point to the same object, whatever object it is, right? Let's call it something OX, then this is the same OX, and the incoming edge to the previous object from L gets killed. Okay. Next, let's say we had L1 is equal to L2 dot F. In this case, let's say L1 was pointing to something or not pointing to something, doesn't matter. Again, I have L2 here, L2 must be pointing to some object here, and its dot F is, let's say, pointing to another object here. What happens after this statement? L1 starts pointing to the object that is being pointed to by L2, the object pointed to by L2, that object's F field, right? So that's what we would do here. We have L1, we have L2, and L2 was already pointing to an object whose field F was pointing to another object, and after this L1 also starts pointing to the same object. Are all of you with me? You should be able to just see a program and keep updating its points to graph at each statement, right? What's the final one? The last statement that we will take care of. L1 dot F is equal to L2. And let's, okay, before that, I have one question here. Is there a guarantee that L2 was pointing to some object before? If it was not pointing to an object before, there will be a null pointer exception here. So you can say that, you can safely assume for now that L2 was pointing to some object before, because if it was not pointing to any object here, that means there would be a null pointer exception thrown in this program. That means the program is incorrect in some sense. Okay. So L2 must be pointing to something, but L2 dot F may not be pointing to something, which means it was pointing to null. Right? So here after this L1 should start pointing to null. So one thing we have ignored in this diagram is that if something is supposed to point to null after a certain point, how do you remember it? Can you propose something? So if this edge, if this box did not exist, I have to somehow record the fact that L1 points to null. Let us say I want to record the fact that L1 points to null. What could I have done? Should I just leave an empty edge? I mean, there is no outgoing edge from it. That's also one option. But then you have to interpret it as follows, that whenever there is no edge going out of a variable, you have to assume that it points to null. Okay, that's one option. Another option is, oh, you create a special node called as null, let us say. Okay, that's another. Universal to all nodes. So let's say whenever you create that guy to this special node called as null. So that's another option. So it depends on how do you want to model a null in your points to graph. Okay. Let's move ahead to the last one. Mm-hmm. So that null node should have special properties, that there is no outgoing edge from that null node, right? It's a sink. There should not be any outgoing edge from that sink, because that's wrong. Null dot F is equal to something. What does it mean? Nothing, right? So that again is an invariant you will have to associate with that node if you create such a node. Make sense? Yeah. Okay, so now under that assumption, now let's talk about L1 dot F equals L2. Again, here if L1 is not pointing to anything, it's a null pointer exception. But if it is pointing to something here, and L2 was pointing to something else here. After this statement, what would you do? Yeah, L1 points to something, L2 points to something else. That guy's dot F starts pointing to this guy, right? So this is how you would update the points to graph over here. Now let's go back to our example. Any questions in this? So this is how the data flow functions that we wrote in the form of the stack map and the heap map could be represented. So this is also a data flow function. Given this statement, if this is the state, this is how you update the state, right? So this is also a data flow function just drawn pictorially, if you think about it, which, and you can represent the stack and the updates to the stack and the heap maps by looking at this. Oh, if you are creating an edge from a variable node, that means it's a stack update. If you are creating a field edge between two objects, that means it's a heap update. The left hand side objects is the index, the first index into the heap map, and the label is the second index into the heap map. And this one is the set of objects that you update it to. There may be multiple edges, so all those objects form the set of data flow values, set of pointer values, set of points to elements for the heap or the stack that you are updating at that point of time. Yeah. No, not in Java, right? So in Java, as we said, you cannot take the address of a variable. So a variable cannot point to a variable, an object cannot point to a variable. Right hand side is always the set of heap objects, right? Okay. If you were doing it in C, the main difference would be that you would be allowed to take the address of variables as well. Okay, so on the right hand side, you may have some variable as well, because you are allowed to do a equals ampersand b, for example. Such variables are called address taken variables. The addresses of those variables are taken using the ampersand operator, and that's the primary difference between how you do it over here and in C. In C, there is one more difference. You have star a equal to b. How do you model it? There might not be a field name, right? Instead of saying a dot f equal to b, you may say star a equal to b, for example. So there you don't label the field, but maybe you want to still create distinction between star edges and non-star edges over there, and so on. Star means one level of dereference over there, right? So it's similar, but some notational differences. I hope you can see that. Yeah. Mm-hmm. Not here. Huh. Huh. Yeah, right. You can't take that. But yeah, go ahead if you had a question about that. Correct. So in C you would have pointers to variables. Yeah. Okay. So let's now draw the points to graph for this. Again, as I said, I'll just keep updating the same points to graph, but when you perform an IDFA, you will have an in points to and out points to graph for each statement. So initially the points to graph is empty. We'll just use these rules to update the points to graph at each step. And I'm sure you don't need to see these rules. They are very intuitive. We can just do it on the fly here. So there is a variable node A that starts pointing to an object after statement 1, and what's the name of that object? It's O1. This is the in points to graph for statement 2 now. What happens at statement 2? Right, so I will first create a new object here called as O2, and correct, with label F, right? This is the out points to graph of statement 2 and in points to graph of statement 3. There is no merge here, so we are just flowing through. Now how does statement 3 update this graph? Yeah, so we create another object here. I'm growing downwards right now. Let's see whether that works, whether we'll have enough space. O3, and this is G. Now at statement, this is the incoming points to graph for statement 4. At statement 4, what update should we do? A dot F dot G. So now how do you find this from a points to graph? A dot F dot G. You just keep following the paths. You don't have to worry about, oh, where is the stack map, where is the heap map. You can just follow the paths. A dot F dot G will give you O3. So let's add an edge from the variable C to O3. So far so good? This goes into statement 5 where we have D equals A. So what should I do? Yeah, so I'll add an edge from D to O1. Now we have E equals A dot F. A dot F is pointing to O2. So let's just put an edge from E to A dot F or O1 dot F, which is O2 here, and then P equals nu A. So there is an object O7, and let's say we have a variable P which points to this guy O7, right? So this is the points to graph at the end of this method. Now one may ask different questions here. So again, I may ask questions like, after line 4, does C alias with A? What does it mean? Do C and A point to, can A and C point to the same object, or at least is a common object there in their points to sets? The answer is no. So you may say C and A do not alias. Similarly, you may say, oh, what all objects are reachable from D? O1, O2, O3, right? So reachability, which things alias with each other, and what points to what and what does not point to what, and all those questions can be answered by looking at this graph, which is stored at each point if you are performing a flow sensitive analysis. Okay. Now a trick question. Can you give me an example, a piece of code where I have a statement like this: L1 equals L2 dot F, or yeah, L1 equals L2 dot F, and I do not know what does L2 point to. It does not point to anything, but the claim here is, it's because I do not know what does it point to, it's actually pointing to something. It might actually be pointing to something, just that I don't know what does it point to. I don't know the object that is pointed to by L2. Can it happen at a statement L1 equals L2 dot F, let's say? Or even simpler, L equals V. Can it happen that you don't know what object is pointed to by V? When can that happen? Give me an example where I might not know the points to set of some variable, let's say, but it does not mean that it's definitely pointing to null at that point of time. It might be pointing to something, just that I am not aware of it. Think about think about intra-procedural versus inter-procedural analysis that we discussed before the break. Correct. So let's say, let's take that example that Keith said. Let's assume V is a parameter, right? Let's say V was a parameter taken by the current function. And if I am doing intra-procedural analysis, I may not have any knowledge about what V point to. It will point to whatever was passed by the caller, right? So if you are analyzing a method independent of its callers, you may not know what all do the parameters point to in the beginning. Similarly, let us say I have a call to a method like we had in the previous session. Let's say I call a method foo and I don't know foo's code. I collect its value as a return value. So I have something like x equals foo, and I don't have foo's code. Now what should x point to after this point? We had said universal set, but then because of that, at some point of time you may see a points to graph where the right hand side is not known, right? So let's say we have such a statement here where L2 does not point to anything in the beginning. What do I do for this statement? If L2 is a parameter, let me write it as a fresh example. So let's say I have a function foo where I take some reference type p as input, and here I say x equals p dot f, some bx is equal to p dot f. Now how should I update my points to graph here? What should we decide? If we are performing intra-procedural analysis, we don't know the methods that we call as well as the methods that call us. How would we perform points to analysis? Given that we want to be sound, that's the main requirement, right? We can be imprecise, but we have to be sound. So what's a sound update on seeing this statement if I don't know the caller? Let's think. Give some options. X equals null is probably not right? Because if let's say the caller is like this, if the caller creates a new object A is equal to new B, and then or let's say A is equal to new A, B is equal to new B, A dot F is equal to B, and then passes it to foo A, right? So if I say it's pointing to null, I'll miss out some information. Later on, if somebody asks me a question, let's say somebody asks me a question, there is another pointer y here, y equal to something, and at some point of time I want to know, can x and y be pointing to the same object? And I'll not have any answer to it. So what answer will I give? If it is null, I would say that, oh, since it points to null, since let's say x, I would say no, x and y cannot be pointing to the same object, which may go wrong, because in reality x may be pointing to some object which is passed through, which is pointed to by a dot f in the caller. So in reality, what does x point to over here? Let's give names. O1, O2, there are only two objects here. In reality, what will x point to after that line? Let's say line number 1, O2, right? So in reality, since I have passed A here, A is pointing to O1, O1 or F is pointing to O2, so x on the heap will start pointing to the same object O2. But then I don't have access to the caller's code right now. How do I soundly perform points to analysis in presence of unknown pointer information? What can we do? Well, SSA is just an internal representation. Let us say this program is in SSA form. This program is in SSA form. In fact, there is nothing here that's breaking SSA, right? Same question may still arise. So let's decide the following. I hope you would agree with the assumption, but if you have any other proposal, please give. Let's decide the following. When we start the analysis of a method, let's initialize the parameters to some dummy object. We don't know what object it is. Let's initialize it to some dummy object so that there is something in it right now. Okay, and let's introduce the notion of, let's call them outside nodes instead of dummy objects. Dummy sounds very dummy. So let's say dummy sounds very silly rather. So let's introduce the notion of a outside node. Okay, an outside node, let's say, is of a red color in this graph. Okay, outside node means it's coming from outside. I don't know which object it is, but it might be something. I'm just representing it over here. So let us say when we start the analysis of this method, right? Let's say the points to graph is not empty in the beginning. We are in this method right now, foo, and as we start, let's say the first thing we do is, from the parameter p, for each parameter that's a reference type, I create an edge to a dummy object or an outside node representing the object pointed to by the actual argument from the caller. Okay, so let's say this is how we start the analysis. So it's not pointing to null right now, it's pointing to something. It could be null, we don't know. It's an assumption. It's pointing to some, we are keeping a representative over here so that we can continue our analysis at least. And now what can we do? If I have x equals p dot f, what do I do? We make another outside node, right? So when we process x equals p dot f, let's create another outside node here. And okay, we should keep giving names to objects. So let's say for this object, I give a name OP in the beginning. Okay, that's just a dummy object or outside node. Now I process x equals p dot f. Again, p is pointing to OP, but I have no more information about OP. It does not mean that OP dot f is pointing to null. It may be pointing to some real object that's passed from the caller. So possibly null, or some set of objects, multiple objects also possible. So let me now create another representative which is pointed to by the field f of OP, and what should x point to now? What should x point to now? That object. And can you propose some name for that object? Some name that makes sense? Yeah, OF is not a good name. Let's choose the following. What line number was this load statement at? 1. So let me give it a name O1. Okay, so we have to choose some name here. At a statement, either there will be a new, or there will be a load, or there will be a store, or there will be a copy. So I can use this name over here, right? Because there is no new over here. So then we can continue with our analysis. If I see now y equals x, I would directly say that y points to O1, for example, and I'll just continue the analysis based on my data flow functions before. Okay. So if I am doing an intra-procedural pointer analysis, I would begin by assigning outside or dummy nodes for pointers, and then I'll process each statement one by one. I'll process them once, I'll process them again in a fixed point loop until I arrive at the same points to graph at each statement, at which point I will say I have achieved a fixed point. I have the points to graph available at each statement, which can be used to derive points to relationships. All of you with me? Okay. Any questions here? And what happens at a join point here? What would happen at a join point for if your data flow value is not the stack and the heap map, but it's actually a points to graph? What would you do at a merge point or join point? Take a union. You will just take a union of both the points to graph. So if I have a statement like this, where I have, let's say I have a basic block like this, and then there is a merge here. This is my control flow graph now, okay? And there is a points to graph PTG1 coming in, there is another points to graph PTG2 coming in from the other direction. I'll take a union, and the in of this node will essentially be PTG1 union PTG2, which means you will copy all the edges from PTG1 and PTG2 into the in of that statement. Okay, so that's just our merge function. So if you want, you could write it formally as an iterative data flow analysis algorithm, right? You need what all do you need to write a formal IDFA for any analysis? Pardon? No, gen-kill were just routines used for live variable or constant propagation analysis. It's not the case that gen and kill are the things you need for each of them. Okay, gen and kill are just utility data flow, utility names given to certain operations. Gen and kill are not, so let me make it clear, gen and kill are not tied to the notion of doing data flow analysis. For example, when I propose pointer analysis, I propose names like stack and heap, or I propose names like variable nodes, object nodes, field edges, normal edges, and so on. Similarly, while doing a certain analysis, if writing the data flow equations becomes easier in terms of two functions called gen and kill, I may put them as part of my data flow equations. Okay, so be clear about this. Gen and kill are not part of the standard IDFA framework. They are just common names given at some point of time. You may see a lot of data flow analysis in future where there won't be any gen or kill. There may be different names given to different things. They may be use and def for some analysis. You don't care about what is generated and killed, you just care about what is defined and what is used at each statement, for example. In this case, what we care about is what is there in the stack map and what is there in the heap map at each statement, and so on. What else do you need? So let's say we have our data flow equations in terms of stack and heap, right? I'm sure you can write those equations in terms of all these pointer graph updates, points to graph updates as well. Other than that, what do we need? Yeah, we need some boundary information. Good. We need to decide what's the initial value. So what's the initial boundary value here? Well, nothing, or you may say that the initial value is the points to graph that includes these special edges from parameters to outside nodes. We initialize by putting edges from reference variable parameters to outside nodes created for each of them, right? So you could say it's empty, but if it takes some parameters, there has to be some initial value for the parameters, and that could be your boundary value. Make sense? Any other? Then the in-out equations that we have already. We know these are my in-out equations. My in-out equations are very graphical here. If this is the in points to graph, this is the out points to graph for this statement. Make sure you understand that there is no guarantee that you have only one in-out equation for defining a full data flow analysis. Your in-out equation may have cases. If the statement is a copy, this is the equation. So your in-out equations may have cases. You write like this, right? In math, when you are defining a function, you will say f of xy is equal to this. X less than 0, then I want to do x plus 1, x greater than equal to 0 but less than equal to some 5, I want to do x plus y. Otherwise, I want to return 0, some such function. So you can have cases like this, right? So similarly, your data flow functions or data flow equations can have cases. Oh, if the statement is, if the statement looks like L is equal to V, then the equation is update stack of V is equal to stack of W, or update this graph as this graph, and then you can have a switch case. So when you write these data flow analysis, typically we would see one of them in the hands-on session. Typically you would have a long switch case, and the switch case checks on what kind of statement are you handling at that point of time, and depending on the statement you may have a different data flow function defined for that statement. Okay, so we have the data flow functions, we have the boundary value. Is there anything else that we need? How do we structure the data flow analysis? We'll have a grand while loop at the top. It says while not achieved fixed point, let's say. How do you detect fixed point? At each statement. So if for all the statements the previous points to graph, the previous out is same as the new out and the previous in is same as new in, then it means you have achieved the fixed point. So you will have a grand while loop that checks for fixed points. Then inside that you would have a big switch case for each statement. If this is the statement, this is the update, this is the statement, this is the update. You keep performing these updates until you achieve the fixed point. Is monotonicity guaranteed here? Is in our flow function? Why? That's finiteness. Yes, so that's finiteness. Finiteness is guaranteed because the number of variables is fixed and the number of objects is fixed. How many variables can I have in a function? It's a finite list given to me in the code, right? And we can even, so many analysis frameworks that we work with, as we will see as well today, impose restrictions like in one line you can only declare one variable, or in one line you can have only one new statement, like what we thought before, right? So under those restrictions you can say the maximum number of variables is the number of lines in my program, so it's a bounded number. The maximum number of objects in my program is also bound by the number of lines in my program, because I have a new statement at each line, I don't have more than one. So the maximum number of objects is finite. What else is there in our data flow values? This node, the number of such nodes is finite, the number of such nodes is finite. Are the number of edges finite? Yes, because if the number of nodes is finite, the number of edges is finite. Are the number of fields finite? Yes, the number of fields is also finite because we have listed down which fields exist in my code. There is one interesting case though there. What if I am making updates to an array? I have an array of objects or an array of structure pointers, for example. So then what's the name of a field? If I do some statement like this is a special case, let's just cover it quickly. If I say a of I is equal to b, where b is some object new a, and A is an array of A type objects. A is an array of some 1000 A type objects, let's say, right? Some number over there. So then this is also a field update, isn't it? AI equals to B. What statement does it look like from these four? L1 dot F equals L2. But what's the name of the field over there? Well, L1 is A, L2 is B, but what is F? Yeah, some index, right? And we don't know how many indices may be there, how many times a loop iterates over, we don't know. So again, we need to create some abstraction. Let us just create an abstraction like this. Oh, A is, oh, what happened? Magnification, okay. So if let's say A is pointing to an array and B is pointing to another object over here, we need to add an edge here, and we might not know what is the range of the for loop. Typically you don't know, it depends on some user input, for example I less than n. So then let's be conservative here because we don't know how many updates are being performed. Let's just add a field whose name is this, indexing operator, let us say. Okay, so we are being conservative here. We are just saying all the indices of this array may point to this object. If I put another object inside the array, I will say all the indices of that array may point to this object. So we have to abstract out wherever we don't know how many things we have to handle, we have to create an abstraction to enforce finiteness. Here we enforce finiteness by saying that all elements of an array are represented using the field square brackets, let's say. So just to continue on the finiteness argument over here, if we do this, then even with arrays, we have a finite number of data flow values in our program. So one guarantee satisfied for termination. The other guarantee is monotonicity. Can we guarantee monotonicity? Given a statement, can it ever happen that while processing L1 equals L2 dot F, one time you deleted an edge and second time you added another edge and third time you again deleted an edge? That's not happening here. You can argue it by looking at each of our data flow functions, that for each statement the points to graph will only grow in a certain direction, and based on that you can argue for monotonicity. Once you have established finiteness of the lattice, the number of data flow values and the height of the lattice, and the monotonicity of your data flow function, you can claim that okay, my pointer analysis will terminate. All right, all of you with me? Okay, any questions before we move ahead to one optimization based on this? Now let's look at a particular optimization called as stack allocation. So where had we said all objects are allocated by default in Java? On the heap. And we had started arguing that not all objects need to remain on the heap. Let's first discuss the following. If I have some capability of finding out a subset of objects and allocate them on the stack frame of their method instead of allocating them on the heap, what all advantages would I get? What all things will I be able to optimize if I am able to identify a subset of objects that I can keep on the stack instead of allocating them randomly anywhere on the heap? How? So I won't call it save memory. I would say you would be able to free up memory without using a garbage collector or without writing a delete instruction. Right now, how are you deleting memory? Either in C++ like languages by writing a delete or free instruction, or in Java like languages because a garbage collector runs in parallel and collects all objects that are not reachable from anybody, and so on, right? I would be able to, both of them are expensive, isn't it? Inserting a delete and free is expensive in terms of programmers' capability, and garbage collection is expensive because a thread has to run in parallel. We are not studying garbage collection in this course here, but it's extremely expensive. Garbage collectors snatch away a lot of resources from your running program for their own operation. Both of them are expensive. If I have an object on the stack, its deallocation is guaranteed free of cost. As soon as the method's lifetime is over, all the objects that are there will just go away. So free deallocation, one advantage. Let's keep writing advantages. Free deallocation. Number two, anything else? Instead of easy, can you add a word that tells that I am optimizing something? Quicker or faster access, let us say, and why? Correct. So in order to get something from the heap, I'll have to make indirections in the heap sometimes, and for objects on the stack, I can fix the address of that object based on some offset to the stack pointer like we were doing for local variables, let's say. So that's faster. Anything else related to faster? Well, faster access because of constant offsets to stack pointer. Faster access because of one more reason. Can you think of cache locality here? Cache locality for objects that are on heap and cache locality for objects that are on stack. Which one do you think you are likely to find early? Yeah, why so? Right, so stack frames are in fact usually small. They fit into one cache block itself most of the times. And since you are running a function, your stack frame is anyway in your cache. If all the objects that you need are also in the same cache block, you will have a cache hit at L1 level itself, let us say, most of the times, right? So you don't need to go to the heap, memory, bring it to cache, incur a cache miss, then go to the memory, bring it again to cache, and then able to access it. If it is on stack frame, most likely you will find it somewhere closer to you already, instead of going to the memory and after hitting a cache miss. So faster access, or rather let me just write, better cache locality, hopefully. I mean, it may happen that some stack frame is extremely large and it doesn't fit in the cache, so the half of the stack frame is somewhere else. It may happen in the worst case, but in general we expect that cache locality will be better for objects on the stack frame, right? So better cache locality, which will also give you performance. Anything else? Number 4, I have one more. We talked about access, we talked about deallocation. What about allocation? How do you allocate objects? You would request operating system and it will give you a free space, is what we had said, right? Here the compiler would tell you while generating code itself, oh, allocate this object at offset number 14 from the stack pointer. You don't have to go and ask the OS to find the space to allocate the object, right? You already know where to allocate it with respect to the stack pointer. So faster allocation as well. What else do we want? Faster allocation, faster deallocation, faster access. That's why we have objects here, right? So stack allocation is a very powerful optimization, and it's enabled by an analysis called as escape analysis. Escape analysis is, well, one very popular analysis for Java programs per se, but in general escape analysis is a variant of pointer analysis. If you have pointer information, if you have a points to graph or the stack and the heap maps, you can directly obtain escape information from there. So let's try to first understand what should the escape analysis do over here. If I am convinced here, let's say that if I could allocate objects on the stack instead of on the heap, it's very good, because I have an O program which is full of objects here and there, and those objects can be allocated faster, deallocated free of cost, and accessed faster as well with better cache locality, in fact, if they are on stack. Now all the objects are allocated using this new statement. How do I identify which objects can be allocated on the stack? Can you suggest? Let's say I have this points to graph for my original program, this one. How many of these objects, if I have to identify which of these objects can be allocated on the stack, what could I do? Or which, rather, let's take it from another point. Which objects is it invalid to allocate on the stack? Why do you need to move an object to the heap, for example? How do you identify that, let's say? Good, that's good. Correct. Correct. So one case is, oh, if an object is never passed to another method, or it's not made reachable from anything in another method. But let me counteract it a bit and say, if I have code like this, I mean it requires a bit more of argument here. Let's see. So let's say I allocate an object. I am in a method foo. I allocate an object here, make it point to A, and I allocate it and allocate another object here, make it pointed to by B, and I pass to a method bar a pointer to the first object. Let's call this O1, let's call this O2. If I don't know bar's code, my claim is the following. Listen to my claim and then tell why is that claim fine. My claim is the following. If I don't know what does bar do, then I will say that O1 cannot be allocated on foo's stack frame. But if I know what bar does, I might be able to still allocate O1 on foo's stack frame itself instead of pushing it on the heap. Can you tell me why? Maybe it was modified as well. Let's make it more interesting. Let's make sure, let's maybe make bar do the following. Let's write bar now. Bar takes P. It does something. P dot F1 is equal to 10. Maybe F1 is an integer field. P dot F2 is equal to 20 something, and that's it. Is object O1, oh, before that, what about O2? Can O2 be allocated on foo stack frame? Yes, because it's not being accessed outside anywhere. Let's make sure that A and B are local variables. Let's say this is A and this is B. So A and B are local variables. If A and B are local variables, then in this program, this object O2, there is no way to access it outside foo, isn't it? So O2 can be allocated on the stack. Very good. At least one object goes on stack over here. What about O1 is what we are trying to discuss here. Is O1 still allocatable on stack frame of foo? My claim is yes. Can you tell why? How does the runtime stack look like? Let's say it grows upwards. I have the stack frame of foo first. In this I have allocated, let's say, O1 as well as O2 now, instead of allocating them on the heap. And there are local variables A and B pointing to them like this. And then I have bar stack frame over here where I have P. Where does P point to? O1. So P points to O1 here. Yes, that's allowed. Yes, yes. So is it okay to allocate it on the stack if this is the code? That's the question. No, no, 10 is an integer. It lies in a field inside the object. We have seen in the morning, right? There is a 4-byte space reserved for an integer inside that object itself. Even if it created a new object, if that object is on the heap, what's the problem? The claim is no problem. Hmm. Right. So let's look at this problem as follows. Is the lifetime of that object required to be more than the lifetime of the allocating method? If the answer is yes, then it cannot be allocated on the stack. If the answer is no, then it can be allocated on the stack. So the lifetime of object O1, is it required to be more than the lifetime of foo over here? Right? It's passed to bar, but bar's lifetime would be over before foo's. Once I am back to foo, I still have the object on foo stack frame and I can access it from here. So under what could I have done such that an object is not allocatable on the stack? If I return the object in here, for example, after this, if I had written this line, return A, what happens now? It should be accessible in the caller. If it should be accessible in the caller, I couldn't leave it over here. Either I should copy it, I should come up with a mechanism that copies the object into the caller, which typically does not exist. So then in that case, we will allocate such an object on the heap. Okay. So if this statement was there in my code, I will allocate it on the heap. That's one case if I return it. Any other? In what more ways can I make it accessible beyond my lifetime? Yes. So let us say I have a global variable here. Let's create some more space here. Okay. So I could have done the following as well. Hey, thanks Mitesh, this is very helpful. I'm sure students, you are also able to see things clearly, right? We don't have to. And yeah, thanks Vijaya for giving that. And in fact, thanks Keith for giving his own Wacom tablet. So we had lots of options generated now. And yeah, good. So now we have this method called now bar A here, which does not create any problem for us. If I returned A, then that's a problem. The other option is if I assign it to a global variable. In Java, you create global variables by marking them as static. So if I had a variable of type A, static A, let's call it GL. And if I did something like this, GL is equal to A, then it's a problem. The object is again accessible outside my scope and hence I cannot keep it on the stack. I should allocate it on the heap. More cases. So let's keep writing down. Returned. So what are these cases for? What heading will you give here? I am just writing it in the space I have. What are these 1, 2, 3, 4 for? Reason not to allocate on the stack. Or just to justify this word, if an object is returned from a method, we say that it escapes its method. So escape analysis basically finds which objects escape their scope of allocation. Okay. So if an object escapes a method by being returned from that method, then it cannot be allocated on the stack. If an object can be assigned to a global variable, If an object is assigned to a global variable, then also it escapes its scope because it can be accessed outside its method's activation record. Number 3, any others? We have one, two, three, we have 4 more. Well, okay, one of them is let's say we can ignore. We have 3 more examples of Java statements which may make an object escape. Yeah, how can you make it referenceable in some other class? That's the question. That's okay. If the method that in which it is referenced is called by me or by my descendants, then it's okay. Its lifetime is still smaller. So outside a class is a syntactic structure, right? At runtime, you may call a method from another class in between and then some other from somewhere and so on. That won't affect as my accessibility of that object, right? What else then? What if I have this? I had a parameter here q and I said q dot f is equal to a. What happens now? When I say q dot f is equal to a and q was a parameter. No, it's always call by value. In Java, there is no call by reference. But we said that the arguments are passed by value. Their fields can be updated. So what it means here, if I perform an update here, in the caller, whatever was the actual argument, that argument was pointing to some object. That object's field is now pointing to O1. Right, which means you can access it in the caller. If you remember the slides example we had that O9 object created in the callee and we had updated it into the caller. In the caller we would be able to access that object O9 after the call, right? So if I assign an object to the field of a parameter, then also it can be accessed in the caller, isn't it? So that's the third case, field of a parameter. Okay, next, 2 more to go. Returned, assigned to global, field of a parameter. I'll help you out. Let's say I have another object here, c is equal to new, I don't know, c, and I say a dot g is equal to c. This is O3, let's say, and that's it. Is O3 allocatable on the stack frame of this method? The answer is no. But is it assigned to a global? No. Is it returned from this method? No. Is it assigned to the field of a parameter? No. That means there has to be a fourth case. What is the reason you said it cannot be allocated on the stack of who? O3. It is reachable from an escaping object. Let's call it this way. O1 is an escaping object because of whatever reason, either global or either being returned or either being assigned to a parameter. But if an object is reachable from another escaping object, then it also cannot be allocated on the stack frame of that method, isn't it? So let's draw the points to graph for this. I won't have to repeat then. Let's see. A is pointing to O1, B is pointing to O2, C is pointing to O3, Q dot F, Q is pointing to some, or let me, for simplicity, let me just remove this. We don't need this case right now here. Let me just remove this. This is the code. There is a global variable which points to A. Global variable points to A, which means it points to O1. And A dot G points to C. A dot G, O1 dot G points to O3, right? Now, can you say why O3 cannot be allocated on the stack frame? Yes, since O1 can be accessed outside foo, O1.g can also be accessed outside foo. So this guy is reachable from an escaping object already. Make sense? You look confused. Make sense? So if an object is reachable from an escaping object, I can access it by dereferencing that object through this field and so on. And hence the fourth case, reachable from an escaping object. It's a transitive relationship here, right? There is a fifth one which is not so important here. The fifth one is if it is reachable from another thread. So we haven't seen this in the course, but just for completion, let us write it down here. If an object is reachable from another thread, in Java you create threads also by creating thread objects, and then you can assign some objects to other threads, fields and so on. So if an object is reachable from another thread, of course it escapes the stack frame, because you know how threads work, right? Each thread has its own stack. So thread 1 has its own stack here with different stack frames. Thread 2 has its own stack here with different frames and so on. So if an object is accessible by a different thread in a multi-threaded program, then it of course escapes the current stack frame. It actually escapes the whole stack and it goes to somebody else's stack. So it has to be on the heap. Okay, so this is case 5, which is not really important right now, but I hope you see the points. So now, can you formulate escape analysis as a pointer analysis problem? Let's say I want to find, for a given Java program, I want to find which objects can be allocated on the stack. We are convinced that allocating objects on the stack is very useful. And if I perform pointer analysis using points to graphs, let us say, what can I do to figure out which objects can be allocated on the stack and which ones cannot? Do what you did just now here, right? Find paths from outside to inside first of all, or global variables, and just check reachability. Whatever is reachable cannot be kept on the stack. Whatever is not reachable from such outside paths can be allocated on the stack. That's it. Escape analysis can be done very easily if you constructed points to graphs and then perform reachability from things that denote outside things. What things denote outside things? Global, returned objects. So if I return an object, maybe I can mark it special. I can just mark it that it escapes by default, and anything reachable from it escapes. If something is assigned to the field of a parameter, again I mark it as escaping, and all other reachable ones can be marked as escaping, and so on. And this way I can identify which objects to allocate on stack. Now, having understood that, the question is, how do you allocate objects on stack? The compiler, as part of its pointer analysis pass, can figure out which objects can be allocated on stack. Now, if you are working with, let's say, C++, which allows you to allocate objects on stack within the language itself, you could maybe transform the code and replace new statements with a stack allocation operation. Or forget C++, let's say Java bytecode. So what are Java programs converted to? Java bytecode. If Java bytecode had different bytecodes for stack allocation and heap allocation, will still be done, because if there is a bytecode called as new h and there is a bytecode called as new s, will generate as part of the compiler. While generating Java bytecode in the code generator pass, we would just generate new s for those objects which can be allocated on the stack based on pointer analysis, and those objects that cannot be, I'll just generate a new h. Well, in Java's case, Java bytecode does not have a new s, new h distinction, but at the intermediate level of the just-in-time compiler, you have options to allocate things on the stack. So there are two options to allocate something on the stack. One, if the language provides it itself, then you can perform a source transformation. You can convert the source code itself after performing escape analysis, let us say. If the language does not provide, then at the lower level, when you make allocation decisions, your compiler might be able to tell the JVM or the runtime in general that, oh, use a primitive that allocates objects on stack for these objects, for these new statements, and the others let them be on the heap. Okay, make sense? So stack allocation is a very useful optimization. There is a small variant of it which is even more powerful. That's the last thing we would study for today. After that we'll move to hands-on. The yes, go ahead. That's a problem. See, that's what we are doing if I pass it to a method that I call. But if my lifetime is about to get over, where's the no, no, not really, right? Let's make it clear. I have an object here which has some field values here, some 10, some 20, some other pointer to some other object or v-table pointer, whatever. And this is on my stack frame right now, right? And stack, let's say, grows towards the top. Now I am about to delete this memory. Where do I move this object? Some people are pointing to it. Maybe some guy is pointing from here within, that's not a problem. But there is somebody else pointing to it from here. If the object escapes the stack itself due to another thread, some other object in some other stack frame is pointing to this object. There is a global variable GL which is pointing to this object. Now what should they point to after this point? Right? You see, I mean, the next address needs to have these field values as well. Yeah, so where should I copy it now? Let's say this stack frame is going to be popped off. Should I copy it to the heap because a global accesses it? Should I copy it only here because only the caller accesses it? It's a valid scheme. What you propose is a valid scheme. I'm just trying to point out the challenges. You may need to know where exactly is it captured. The opposite of escape is captured. Where is it captured? Is it captured in the caller's frame, or is it captured? Maybe the caller also returns it to its caller. So is it captured in the caller's frame? Is it not captured on the stack? Is it captured directly in the heap? Then anyway, so it may happen that if you do this, what's your name again? Shreyas. So what if you decide to come up with such a scheme, it's possible that you may have to incur a lot of cost in finding where to allocate it. And it seems in many cases, let's say the case where it's accessible by a global, you may end up saying that, oh, after doing all that costly analysis of its lifetime, I know that now it can't be allocated on any other stack frame, so I have to anyway allocate it on the heap, right? And once you allocate it somewhere else, you can't just keep it there. You have to update all these references. This guy should not point to this guy, now it should point to somebody else. This guy's reference should also be updated. There is a reference on this frame, maybe there is a reference on another frame, and so on. So we actually do it in one of our works where we try to allocate objects on stack if we have more confidence that we don't have to move it. But if we need to move it, if because we were wrong, we have to incur all this cost, right? So better to not do it for every object. Maybe do it based on some other information about the object, that okay, I know that it's a tentative candidate for not going on the heap, but let's talk about that later. Any other questions? Okay, so finally there is a close cousin of this optimization called a scalar replacement. That's the last topic before we move to hands-on, as I said. Okay, scalar replacement is an interesting optimization. It says, okay, so what we got rid of deallocation became free, cache locality has improved, field access is faster, and allocation is faster. But there was one more overhead about objects that we talked about in the morning. Remember what was that? 12 bytes of the header, right? That's extra memory for every object, which is huge. So can we get rid of that memory by just getting rid of the object altogether? So can we get rid of an object completely? That's the question. Scalar means scalar variables, simple variables instead of objects. So object is a complex data type, so complex ka opposite is scalar. Scalar variables are normal variables. Can I get rid of an object and replace its fields with scalar variables? That's what is called scalar replacement, right? So if I have an object like this, let's say A is equal to new A, and let's say class A has two fields, int x and int y. I may be doing something with them here. Let's say after this I say a dot x is equal to 10, a dot y is equal to 20, and then I do something here. P is equal to under root a dot x square plus a dot y square, and then I print p on the screen. That's it. This is my method foo. So now the question is, does this object, let's call it O1, does O1 escape foo? First of all, is it stack allocatable? Yes, it does not escape foo, it is stack allocatable. So I could have allocated on the stack and got some benefits. But the point here is it is also scalar replaceable. I am not using any other property of the object that depends on the header. Okay, we'll tell about those properties, but let me tell you what is scalar replacement to begin with. I could have rewritten this code as follows. Let me just mark this O1 somewhere else inside. Now I could have rewritten this code as follows. I could have written foo as integer, let me call it a underscore x is equal to 20. It's just a variable, scalar variable. Integer a underscore y is equal to 20. P is equal to square root a underscore x square plus a underscore y square, and print p. It is perfectly possible for me to write code like this, isn't it? I don't even need to allocate the object. I can just replace it with scalar variables. This optimization is called scalar replacement. Now let me make a statement and then ask you for inputs. Not every stack allocatable object is scalar replaceable. There could be an object that I can allocate on the stack but cannot replace with scalars. Can you tell me an example where that would happen? Tell me some Java statement because of which the object is stack allocatable as this one O1. Here it was stack allocatable as well as scalar replaceable. I would be able to rewrite code like this without ever allocating an object. This new got deleted itself. Forget about stack or heap. It just got deleted. No object allocation here, just local variables. So no 12 bytes header, nothing else. But good. So as pointed out, there are cases where if those statements exist in my program, I will not be able to replace it with scalars. What if there was a statement here that said, let's say, apart from printing p, I also had passed it to some method bar. What would be the prototype of bar? What does it expect? What kind of argument does it expect? No, not p, sorry. Let's say it is a. So what kind of an object, what kind of an argument does bar expect now? An object, right? It expects a pointer to an a type object. If I remove the object allocation, I have no object to pass it to. So I cannot, by default, I cannot perform scalar replacement. Could I have done something better? I might have created another copy of bar. If bar does not let that object escape further, I could have created another copy of bar which expects integer variables instead of references. And if I am able to create such a copy of bar, I will call that bar instead of this bar, and I will still get scalar replacement done. This is a project that one of my MTech students is doing right now. But there is one more situation under which you would be able to scalar replace this object. What if bar is inlined? Have you heard of function inlining or method inlining? So what if the compiler decides to inline this method? If it inlines this method here, the call to bar is gone, but it's possible that it still escapes. Maybe bar was taking a parameter as input and assigning it to a global. In that case, you cannot scalar replace it. But if bar was just reading the field and printing it on the screen or doing something with it, not making it really escape, then I can, after inlining, still perform escape analysis and allocate it on the stack, or make it scalar replaceable, and so on. So again, this you see here an interesting dependence. If you perform pointer analysis or escape analysis after performing method inlining in a compiler, you may be able to get more optimization opportunities like any other optimization. You may be able to do more constant propagation after inlining. Similarly, you may be able to do more scalar replacement after inlining, and so on. Okay, hope that makes sense. So that's the idea here. In general, a compiler that optimizes such programs would try to perform the best optimization first. Let's say try to identify which objects can be replaced by a scalar. Method call is not the only thing. In Java, you have statements like if a instance of foo or a instance of some other type t, an instance of check requires to know the type of the object. The type of the object is stored in the header, because in the header you have a pointer to the class metadata and so on, which tells you which class of an object it is. So if you want to check, you want to perform an instance of check, again you cannot replace it with a scalar. You may be able to allocate it on the stack, for example. So first identify objects that can be replaced with scalars completely by performing escape analysis. Then maybe find, oh, if those which cannot be scalar replaced, can I stack allocate them? I still get the other benefits of stack allocation. If not, leave them for heap allocation. And maybe do this again after performing any method inlining. If the compiler decides to inline a method, or the JVM decides to inline a method at some point of time, maybe perform this analysis, one more pass of the same analysis, to see if you can optimize accesses for more objects, right? So that's what a typical compiler would do here. Just to complete the discussion, there are scenarios in which you may not want to do stack allocation or scalar replacement. Can you think of some? You can, but you will not, or you may not want to. When can you think of some example? So let's say you did pointer analysis and escape analysis and find out that these 4 objects are local, they can be kept on the stack. These 2 are even scalar replaceable, and the remaining 5 are escaping and they can be kept on the heap. But it may not be a good idea to allocate all of them on the stack. Mhm. Correct. So if you are just creating an object again and again and again without deallocating the stack frame in a recursive call, or if it is a large array, if the object is an array with 10,000 elements, you may not want to increase the size of a stack frame so much. Well, many languages don't even allow you to flexibly change the size of a stack frame, but even if they do, you may not want to do it, because growing the size of a stack frame may have impact on the cache memory, for example. Now the stack frame doesn't fit into the cache block, for example, and you may have a loop inside the stack frame, so you actually want to refer to different parts of your stack frame again and again, and things like that. So typical compilers will take care of such corner cases. They will see if it is an array, they may say, oh, don't even consider it for stack allocation. Or if they found that the object is being passed to a method which is recursive, they may say that, oh, let me not allocate it on the stack, even if it can be, and so on. But otherwise, stack allocation is a very useful optimization. It's performed by almost all O compilers. There is an interesting language called as Go, which takes an even different route. Has any of you programmed in Go? Or at least have you heard of this Golang, the language Go, right? Or Golang? There is an interesting approach they do. I found it just last year and we studied it in detail, and one of my students is doing something interesting there. So what Go does is, it by default keeps objects on the stack, not on the heap. It says by default everything is on the stack. The compiler performs an analysis to, again it performs escape analysis to find which objects cannot be kept on the stack, and hence the compiler, while generating code, generates an instruction to copy those objects on the heap. Okay, so that's a very different approach. Java allocates everything on the heap and decides which can be allocated on the stack. Go says at the programmer level, everything programmer should assume is on the stack, but the compiler will try to find out which of them are not safe on stack and move them conservatively to the heap. And so that's a very interesting direction of thought too. Anyway, we'll close this discussion now. Can we take a tea break now, or we'll wait till 3:30? Okay, sure. So we'll take a tea break now. We'll meet again. Let's meet in less than 30 minutes, 25 to 30 minutes. We'll continue with the hands-on session. Any questions? Okay.